Okay. Thank you for letting me be here and give this presentation. This will be fun for me. I'm Mark De Kleine. I'm a graduate student at Washington State University in the Agricultural Engineering and Biological Systems Engineering program. This is a picture here of Prosser, Washington, where I live. Now, Prosser, Washington is not Washington, D.C. Point A right here is Prosser, Washington. Point here is Washington, D.C. It's about 4,200 kilometers from there. Here's an aerial view of Prosser, Washington. It's marked here on A. You know, I just want you to notice the green all the way around the state of Washington. This is all grapevines, apple trees, peach trees, pear trees, cherry trees. And if you notice, this is not the rain that's causing this green. This is all man-made. You see these circles down here. All of this is irrigated water from humans. This is definitely in the desert. It's like a greenhouse, so it's a nice place to grow. The area that I grew up in is called Grand Haven, Michigan, and this is about 3,100 kilometers from Prosser, Washington, where I live here. Marked on B is where I grew up. I'll show some pictures here at Grand Haven. We're surrounded there by Lake Michigan. Here's a sunset that you can see typical in the summertime. This is what the pier looks like in the wintertime. Lots of frozen ice with waves that crash over it. It's pretty spectacular. And here's an aerial view of Grand Haven, Michigan. So the first thing I want to talk about today is my master's thesis, and this was done at Michigan State University by myself and Dr. Dan Geyer. And the title of it is Development of Vacuum Harvesting Techniques for Chestnuts. And I hope I got chestnuts right here. I used Google Translate, so I hope that's right. This was a picture taken in central Italy in the fall of 2010. As you can see, some of these trees, this tree right here was about 500 years old, and it would take about 6 of us holding arms like this to go around the tree. That's pretty impressive. These are some pretty good-sized trees. So the chestnuts, what are they? The chestnut grows in burrs. These, as you can see in this top right-hand corner. And the chestnuts inside, hopefully you're familiar with those. When you harvest them, or when the chestnuts are ready to harvest, they fall to the ground. And so you pick them up off of the orchard floor. And when you're harvesting, you have chestnuts, burrs, debris, leaves, twigs, all this kind of material that you're harvesting as well. So it's a problem to get the chestnuts out of this material. Here's some consumption data around the world on chestnuts. And Korea leads the way, Japan's right behind them, Europe, China, and then here in the United States, it's very small chestnut consumption. That's due to a blight that came through and wiped out all the American chestnut trees. But if this consumption here goes up to 1 pound, the United States would have to have over 100,000 acres of chestnuts planted, which would mean that there's a lot. Current chestnut harvesting methods are either handheld tools, picking them up by hand, or some brooms that people use. Mechanical sweepers that have been adapted from hazelnuts, coffee beans, walnuts, pecans, and these are mechanical sweepers, and then a mechanical and vacuum combination machine. Here's me driving one of the mechanical vacuum combinations. You can see these paddles right here on front, windrow material into this collection tube. Now, when all this material goes up into the machine, it takes a while for all this to be processed. This is an 85 horsepower machine, so it's pretty complex. It's pretty big. The objective of this research was the statement that we made is a vacuum harvester can be designed to harvest chestnuts using a single stage system. The technique should sort the field debris from the chestnuts while minimizing the chestnut loss. And then we needed this system to be economical for smaller sized orchards, not big scale orchards. So the process and techniques into vacuum harvesting. The initial parameters we need to know are physical properties of the chestnuts and debris themselves. So we have chestnuts, burrs, and debris. Here we'd like to know aerodynamic properties of this material, being the terminal velocity, which is air required to suspend or float material in the air, saltation velocity, which is the air velocity that's needed to convey material down a tube, which is different from the terminal velocity, and then also a solids velocity, which is the ratio of airspeed to the speed of the material, and then also the physical properties of the chestnuts. For the system requirements, we need to know some air and vacuum requirements, and then also the engine requirements for the entire system. Here, total system pressure drop and fan requirements is efficiency for the vacuum, and then engine speed or power transmission is important. So we'll talk a little bit about horizontal conveyance. Here there's 3 phases. There's a dilute phase, which is theoretical or ideal. That's where material would travel inside of a tube and never touch the wall. It doesn't have to happen in reality. The next is a dense phase, where you see the majority of the material moving along the bottom, but it's not into bed formation, which is the next one. What the system we designed here was looking or focusing in on the last two phases here. So if we take the dilute phase transport, that's related with terminal velocity. Now, if we know that there's bed formation along this tube, can we use that to our advantage? Well, what if we take this dense phase transport and now tilt that on an angle? Can we actually encourage bed formation? And this is a system we came up with. It's called a saltation sieve separator. So here's a picture of it here of the test in the left-hand corner. And again, here's that picture there. So the saltation sieve separator is designed to remove chestnuts from an airstream in a single step. And it manipulates the momentum of the chestnuts and the material itself using different air velocities. And it forces material interaction, and it capitalizes on the effects. Material flow is this way here. So material flow is that way. There's momentum transfer skids, which are these right here, which were used to slow material and force the interaction, and then also give a spot for that bed formation to drop out of the airstream. And there's also a hinge paddle that was used for ensuring that everything was obstructed. We didn't want any material that had a clear path from front to back. It also did some other things with the velocity point of the air. The system itself was characterized based on 2 performance parameters. One was the chestnuts loss, which was the amount of chestnuts that went into the system compared to the amount of chestnuts that came out, and then also the separation efficiency. How well did it separate the chestnuts from all of the other stuff? So I used a box banking design for my experiment, and without too much detail, what this is 3 independent variables that I chose, and they're coded in 3 different levels, usually a low, medium, and a high. So the chestnuts I quantified into quantities, 20, 60, 100, a differing amount of debris, and then a feed rate into the system. And so a mixture was created with each of these different parameters and then fed into the system, and the results came out. Now here's a lot of the data that came out of the system. But if you notice down here where we have a maximum number of chestnuts entering the system, you can see that the chestnut loss here is relatively low and the separation efficiency is pretty good. Actually, when 100 chestnuts entered the system at a fast feed rate, we had 1.3% chestnut loss, which is pretty good. We can maximize the number of chestnuts coming in and lower our chestnut loss. I used a response surface methodology to show these points even more. So this is chestnut loss based on the number of chestnuts entering the system and the amount of debris. As you can see, when the number of chestnuts is high, here we're averaging about 5% chestnut loss. Same with separation efficiency. The x-axis is number of chestnuts, the y-axis is the debris, and you can see this mound right here where there's a maximum separation efficiency, and this is occurring when a large number of chestnuts are entering the system. This is for chestnut loss versus the feed rate and the separation efficiency. And again, here we can see this low chestnut loss here at a maximum number of chestnuts and high separation efficiency at a maximum number of chestnuts. So a model that came out of the system here is presented in this table here. If you notice, the number of chestnuts here really had the only significant estimate of the coefficient. So the rest of the parameters did not. And some conclusions for this system were the saltation sieve separator technique can be used for separating chestnuts from an airstream. If you want to minimize chestnut loss, you want to maximize the chestnuts going into the system, and likewise for the separation efficiency. All right, I got a minute, so I'm going to try to get through this really quick. This is what I'm working on right now. This is design and development of apple harvesting techniques. And this is a picture here at Washington State University in Pullman. This is my current project right now. 13 to 14 billion times a year in Washington, somebody reaches out and grabs an apple and brings it back. That's a pretty big number. Labor costs are increasing. There has to be some sort of solution for this. The objectives of this research is to design and develop prototype techniques for harvesting, and again characterize the efficiencies of each of these techniques. The novelty of this design is that it is designed for the fresh market. It's very important to growers in Washington, and it uses the bio-yield limit for compression and applied force. Again, it's bulk harvesting using a precision application. So this is the first prototype, and it's called an apple equator. It has flexible rotating rubber cylinders right here, and this is expandable. This whole cage is expandable, so it can collapse onto apples. And what I want to do is use as many off-the-shelf components as possible. This is what apple orchards look like in the state of Washington. They're grown in these planar canopies like this. This is as long as you can look down, and you can see these, where the apples are growing along these trellis lines. So theoretically, it may look like this, right? Now, what I want to do is put my end effector in this region here, collapse onto the apples, and harvest them that way. Here's some more examples of how this particular prototype will work, and this will spin the apple around the equator. The next one is the apple vert is what I call it. It's very, very similar. This looks similar, except you notice the cylinders are replaced with rotating wheels. So now instead of spinning the apple around the equator, I'll spin it vertically. It's very similar to how people pick apples in the state of Washington, or anywhere else for that matter. So again, here's the system prototype of how we expect it to work. The measurables here are going to be the harvest efficiency, which is going to be collected fruit versus missed fruit, damage rate, the percentage of fruit that's good to no good, and then eventually some throughput, field capacity, some apple units or bins per time. Maybe this might be the future. We never know. Here's a website right here of the group that I'm in, which is called the CPAS group at Washington State University. You guys can check it out. There's a whole bunch of articles on all the research that we're doing, and that's my email address if you want to get in contact with me. So thank you.
With chestnuts, when you buy chestnut in Europe or China, they're quite small, and ones here in Japan are quite large.
Uh-huh.
The ones you were measuring in the sort of the size range, which type of chestnuts were you measuring?
Yeah, so we have two varieties that are typical in Michigan. There's the colossal chestnut, which is a European-Japanese hybrid, and then there's the Chinese chestnut. We were using the colossal, which are the larger of the two. The Chinese chestnuts that we grow in Michigan are a lot smaller than the other ones. I did not see, when I chose the chestnuts to go into the system, I did not include or exclude based on size. So we had a range of of chestnuts that went in. But typically they were the larger, maybe 25 millimeters.
Anyone else?
Thank you. You mentioned about the separation rate of 60 or 70%.
Uh-huh.
What happened with the rest of 20 to 30%?
The rest of it ended up in the collection chamber. And now we determined that chestnut loss was first important. We did not want to lose chestnuts. After that, the process that happens after harvesting is the chestnuts are then put into a water tank. So the 20% or 30% that was missed ended up into the collection tank. So it was just that you had more material that was collected. Put it into a water tank, and what typically happens is we scoop off the top. So,
I'm very interested in this about when you maximize the incoming chestnut to the machine, you can improve the decrease the loss and also the expression, I think. But how we maximize, because we harvest, so there should be some chestnut in the field and then we harvest. So how we maximize things, maximize the incoming chestnut?
sure. Maximizing it would be the best if you can windrow material. So if you can windrow into, into a specific collection device, that would help to maximize, rather than one here or one there or one there.
Anyone else?
For the apple project, I'm not sure because some type of apple is not really round.
Mm-hmm.
Like red delicious is some like yeah, a bit like a box.
Sure.
It will, I mean, it is not really round. All the surface will experience different pressure.
Mm-hmm.
How you deal with that?
Okay, so the pressure, the collapsing pressure, like this, is going to be based on a bioyield point. So bioyield is a relationship between stress and strain, and right at the point where cell failure occurs, that's where the force drops off. So I will limit that pressure based on the pressure that's coming back. If it starts to collapse more than that, or the bioyield point, or that force goes above the bioyield point, then I stop, open back up, and close in a different region. Do something different with the fingers.
I have a question for apple harvesting mode. In your slide, apples with lines, so it is very easy to pick up by your indicator. But actually, apple does make your lines and leaves randomly, not make a line. So how do you harvest in apples?
Sure. There's two different types of orchards. The orchards that I'm going after right now are the ones that are grown in a line. There's a lot of input that goes into these orchards to get the apples to grow in certain regions. Now, if you go into a traditional architecture orchard, where the limbs are just going off randomly, then it's going to be definitely a different system to harvest. Not to say that we won't try this on those, but it is a completely different system to harvest in. And it's right. It's not theoretically. What I showed you, they're all in a line. That's not how it works. There's branches, and some of the apples grow this way, and some grow that way. But I think that'll be taken care of with the movement of the end effector itself.
They have a V shape.
Sure.
That's
Yeah.
the fence style.
Yep.
So can you make the convince farmers that the uniform, planting systems? That's the point to introduce the such a robot system.
Sure. As long as I can get this window where we have some growth right here and some growth right here, to me it doesn't matter if it's this way this way, as long as I can get this window, it doesn't matter to me which way they grow. To me, that'll all be the same.
How many percentages of farmers have such this one? Or
Sure. Sure. That's the ultimate question. Right now, anybody that's planting new orchards is planting them this way. All of the old orchards are in the traditional. It's not a lot, but it's moving towards that way, specifically because there has to be some solution for harvesting. They realize that in order to do that, horticulture has to go along with engineering, and so that is the future.
The yield is quite similar with the conventional way.
Actually, there's a lot of people that say the yield is a lot more because you're not taking up as much space with a round tree where the apples are just growing around on the canopy. You're really maximizing your orchard area or leaf area to the specific density of fruit that you can grow in that area.
How much farmers have to pay for the train?
Yeah. I think it's don't quote me on this, but maybe $20,000 to $25,000 an acre. It's pretty expensive. It's pretty expensive up front.
Yeah, that kind of horticultural technologies and engineering should be merged or fused, and we may step for automation and automation.
Yeah. Yep.
Anyone else? Okay, thank you very much.
Thank you.